Next, we'll show what the wave function looks like for the zeroth order polynomial. So we'll call this one psi 0. And for the zeroth order polynomial, this would just be some amplitude times that Gaussian, since the polynomial has no factors of x in it. We'll show that this shows the Schrodinger equation everywhere. And in addition, we'll find out that there are constraints on the energy E for this particular eigenstate. E0, we'll call it. So remember that the Schrodinger equation is minus h bar squared over 2m t squared psi tx squared plus u of x times psi has to equal e times psi. From our work before, we already know what the second derivative is. Here in this parenthesis, we're going to put minus 1 over a squared e to minus x squared over 2a squared plus x squared over a to the fourth e to minus x squared over 2a squared plus 1/2 kx squared is the potential. All of that equals energy times psi. Okay. Now we're going to let all the factors of this exponential drop away. And we have minus h bar squared over 2m 1 over a squared. That's this first term. So that will become plus minus h bar squared over 2m 1 over a to the fourth times x squared, and then we have plus 1/2 kx squared equals energy. What we saw before is that these two terms will actually cancel one another because of our constraint of what the constant a is allowed to be. A actually worked out to be, or a to the fourth actually worked out to be h bar squared over m times k. So that actually made these two terms cancel. And notice that they're both proportional to x squared. So now we have that E naught to h bar squared over 2m 1 over a squared. Now I'm going to remember what a squared is. A squared is h bar over square root of mk, k being the spring constant. So this works out to be 1 factor of h bar left up here, with a 2 down there, there's a square root of k over m. Now if you remember for the harmonic oscillator, square root of k over m has a significance, or we see it written a different way. That the natural angular frequency is always equal to the square root of the spring constant over the mass of the particle. So if I have a mass hanging on a spring here. It goes up and down as a superharmonic oscillator at a certain angular frequency, and that angular frequency is equal to the spring constant divided by the mass, take the square root. So we see for this lowest energy eigenstate that the energy is 1.5 h bar times this angular frequency. And what's interesting about this is even the ground state energy even the ground state has an energy associated with it, and that's quite significant. It's a lot like what we saw with a particle in a box, that even a particle with the ground state has to have an energy associated with it, and that was seen as consistent with the uncertainty principle. Same is true here.